we won't be discussing these topics in the kind of level of depth that is required for JEE, because that is not what is expected at the KVPY first level. We will be looking at a more basic level, which is required for the KVPY, and then of course you will be doing these topics. Yeah, that Hemant sir was teaching. I know he will be continuing with that section again when his lectures uh, continues. Okay, so center of mass and collisions, etc., will continue with Hemant sir. Uh, my track will be different over here, so we will start with optics today. So this is a class 12 topic, so that is why this will be studying at a more basic and fundamental level compared to what you require for JEE, but it will be more than sufficient to cover the questions at the KVPY level. Okay, so optics is divided into two sections. Okay, the first is called ray optics, or also geometrical optics. Okay, where essentially the properties of reflection and refraction are studied. Okay. And at this stage, you can just treat the laws of reflection and refraction as experimentally derived laws. Okay. But as a general background, you should also know that light as a phenomena, it has two types of behaviors. Okay, light has one behavior which is the wave nature. Okay. So light as a phenomena is electromagnetic wave. Okay. But it has another type of behavior which is the photon, or sometimes people also call this the particle nature. But the term particle is not very apt actually. The photon theory of light, or the photon behavior, is the better description of it. So wave nature of light is responsible for all the phenomena like reflection, refraction, also diffraction, interference, polarization, various properties of light like this. Yes. Whereas the photon nature of light is responsible for something called photoelectric effect, okay, which is basically generation of electricity from light. Okay. So that's where photon, okay, nature of light exhibits its properties. Then also the interaction of light and matter at the atomic level. That is where light exhibits the property of its, you know, uh, photon nature or photonic nature. Photons are small packets of light energy which have momentum and energy, but which are massless. So just as a general information, you can write this down. So photon is what we call a quantum, or a packet of energy, okay, and that is electromagnetic radiation energy. Okay. It has energy equal to hc by lambda and linear momentum equal to h by lambda. But zero rest mass. Optics is the study of light, both experimental and theoretical. So the first part of optics is ray optics or geometrical optics, which is the study of reflection and refraction. And as I have explained here, reflection and refraction actually comes from the wave nature of light. It is a consequence of light being wave. Yeah, so zero rest mass means they are particles or they are packets of energy which do not have any mass. Rest mass is a term that comes from relativity. Okay. In relativity, in relativistic mechanics, mass in general is a dynamic property. Okay. So that means mass depends on motion, which is something very different to what we understand in classical mechanics. In classical mechanics, the mass or inertia of a body is independent of its motion. But in relativistic mechanics, which is basically mechanics of particles moving at very high speed, we understand that mass varies with velocity. So you might have seen this famous equation, part of Einstein's relativistic theory. It gives you the formula of what is called dynamic mass. So this is c is speed of light. So c is 3 into 10 raised per 8 meters per second. So what happens in Newtonian mechanics? Dynamic mass doesn't come into, yeah, mass of moving electron can be treated like that, but moving electron in an atomic situation does not really move anywhere close to the speed of light. So the mass is more or less equal to, dynamic mass is more or less equal to the rest mass. Okay. So for any particle or body moving at a speed which is very less compared to the speed of light, okay, including orbital electrons in atoms, V by C is negligible compared to 1. So M becomes equal to M naught. So that is why in classical physics or in classical mechanics, which is the kind of thing we are studying in Newton's laws of motion, collisions, work by energy, etc., we don't take this equation into account. Okay, this equation becomes important only in high energy physics where subatomic particles are accelerated to very, very high speeds, close to the speed of light. Then this becomes important. Okay. So for example, if a particle is moving at what is a very, very high velocity, like let's say 1 into 10 raised power 5 meters per second. Now, this is extremely large velocity. This is something like 100 kilometers per second. Okay. But even then, V by C will be 1 into 10 raised power 5 divided by 3 into 10 raised power 8. So it will be something like 3.33 into 10 raised power minus 4. So 1 minus V square by C square will still be like 1 only. Okay. So the mass of the particle will still be equal to rest mass. So that is why in most of the cases that we consider in physics, the relativistic mass does not come into the equation. The dynamic mass concept does not come into the picture. It is only significant where you're talking about very high energy particles moving at speed close to speed of light. So this is significant. It's called high energy physics. Okay, very close to the speed of light. But at the same time, we should also understand that photons, they don't come under the category of particles because their rest mass is zero. They are not particles because their rest mass is zero. Photons, they are packets of energy. Yeah, Pratmesh, you will have to be a little faster in these lectures because these are KVPY lectures and a lot of things to cover. So I will give you an overview of some of the topics, and you always have the opportunity of reading more about this from reference books and things. Okay. Yeah, find out about that, Ayusha. Like I said, okay, these are this. If you have an interest in physics, okay, and you're planning to give exams like KVPY and Olympiads and all that, then you should have heard about Higgs boson till now. If you've not heard, then find out about it. Okay, it's a very famous particle. So anyway, now let's come to the topic for today. This was just some general information. So the topic for today we'll be starting with is ray optics or geometrical optics. Both the names are equally significant. So the fundamental properties of light that we'll study in this are reflection and refraction. So you already know the laws of reflection. That is, in any situation, the angle of incidence is equal to the angle of reflection. And the incident ray, the reflected ray, and the normal are coplanar. They lie in a common plane. Okay. So this can be visually depicted by, if you're talking about reflection at a plane surface or what is called a plane mirror, and we have a ray of light which is incident like this. So you know that after reflection, its path becomes like this, such that at the point of incidence, if you drop a normal to the mirror surface, then the angle that the incident ray makes with the normal, that is called the angle of incidence, and the angle that the reflected ray makes, that is called the angle of reflection. So angle of incidence is equal to angle of reflection. And these three lines, the incident ray, okay, the reflected ray, and the normal, they lie in a common plane. In this case, this is a vertical plane, and that's why they are coplanar. Okay. So this is reflection at a plane mirror. Now this idea can always be extended over here, that suppose we have curved surface which is polished. So this is an example of a curved surface which is reflective in nature. Okay. And again we have a beam of light which is incident at some point. So in this case, how will we find the reflected ray? So what we'll have to do is, at the point of incidence, we have to drop a normal. Okay. So this is the normal to the surface at the point of incidence P. So you have like a tangent plane, and perpendicular to that you have the normal axis. And then your reflected ray will be such that it makes the same angle with the normal, that the incident ray. So this is how the principle of reflection gets extended from the case of plane mirror to any general case. So there is a proof of this law also, but it is based on a wave optics property. So we will not get into the proof over here. We just treat it like an experimental law. Okay. And we'll concentrate more on the applications of this. Okay, so for example, when it comes to reflection at a plane surface, okay, you know that any point object, its reflection becomes a point image which is behind the mirror at the same distance. Yeah. So for example, if we have a point object, okay, and an observer who is viewing this from here, then what happens is that any set of rays which are emanating from the point object, after bouncing off the mirror, okay, after reflecting off the mirror, they appear to be coming from a virtual point behind the mirror, which is at the same distance behind the mirror as the object is in front. So if this distance is x, this distance is also x. So what we see is that the point object, it produces a virtual point image I, okay, at the same perpendicular distance behind the mirror. Okay. And it doesn't matter whether our observer is here or our observer is here or our observer is here, they will all see the same virtual point image, because all the reflected rays, they, when you produce them back, they appear to be coming from the same virtual point. Okay. So now when we extend this idea to the case of an extended object, like an object AB over here, what happens is that all the rays emanating from AB, from all points everywhere, they all reflect in such a way, creates a whole field of reflected rays, such that the image of AB now appears to be like this. So it's always of same size, it is always vertically upright, and it is always the same distance behind. So any extended object like AB over here, it is reflected by a plane mirror such that it produces a virtual image A prime B prime. Now this virtual image has the property of being same size, okay, upright, okay, then what we call laterally inverted. So laterally inverted means what? That right and left side are inverted. So for example, the image of the letter E will appear to become like this. The image of the letter P will become like this. So this is the meaning of lateral inversion. Okay. And of course it is at the same distance behind the mirror. Okay. So these are the properties: same size, upright, laterally inverted, and same distance behind. Yeah, Sarvesh, I will be providing you with the notes, so you don't need to take that much time to write down each and everything. Okay. As I said, the KVPY lectures are a bit like introductory for the class 12 topics, so we'll be going a bit fast. And you always have the opportunity of going through these topics from H.C. Verma or any other reference book. Okay. So we'll be concentrating more on the applications here. Okay. In any case, these are things that you're familiar with, class 9, 10th level. Okay. Now let's come to some application type of situation. Okay. Now, for example, one very common type of situation that you can be asked at KVPY level is when there is relative motion between a mirror and an object. Okay. So let's start with something simple. So we have a plane mirror like this. Okay. So if this is the XY plane, so this is a plane mirror which is parallel to the YZ plane. Okay, so that is the perpendicular to the plane of the diagram you can see. Okay, the board's plane or the whiteboard's plane is the XY plane. Now we have a point object over here which is moving with a velocity. It's moving with a velocity which is like this. So this is the velocity of the object. So a point object in front of the mirror moves with a velocity of, let's say, 3 I cap plus 4 j cap in meters per second in the xy plane. Okay. Find the velocity of its image. Okay. And secondly, the relative velocity of its image with respect to the object. Okay, just try this out, people. So this is a simple kinematics type of question. You have to just correlate the concept of reflection that we've just understood and kinematics that you've been studying for quite a few months now. Yes, very good, Harsh. That's correct. Yes, Nikita, your answer is correct. Harpriya, your answer is correct in magnitude, but you have to give in vector form. Shubham, your answer is correct. Yes, Harsh, your second answer is also correct. Okay. So first of all, let me give you the answers, then we'll discuss. No, the velocity of the image will be like this. It will have an x component which is minus 3 I cap, but a y component which is plus 4 j cap. And that is why the relative velocity will become minus 6 I cap. Okay, so let's understand why this happens. Okay. Remember, the mirror is in the YZ plane. Okay, so that is the significant thing. So if you have a plane mirror in the YZ plane, now suppose an object is originally here, so its image is here at a distance x behind. Okay. Now after some time, let's say the object moves here. by some distance delta x. It moves to O prime. So this distance now becomes x minus delta x. Okay. So what will happen? The image will have to be here now. Now the image will have to move by displacement of the image will become minus of delta x now, because this distance will have to be x minus delta x again. Okay. So what this tells us that any x component of velocity that the object has, the image will have to have equal and opposite x component of velocity. So if the velocity of the object is vx I cap, the velocity of the image will become minus vx I cap, because the mirror is in the yz plane. Okay. So this will also apply as an equation if it is like this. The object is here, the image is here. Again like this, if the velocity of the object has an x component like this, the velocity of the image will be like this. Okay. If the object is moving away, then the image will move away like this. Okay. So that's the first thing. Now the other thing is that supposing in the same situation, the object has a velocity like this, it's parallel to the mirror. Okay. So after some time, so right now the object's image is over here, the same distance x behind. Now after some time, let's say the object moves here by some distance delta y. So the image will also have to move here by the same distance delta y, so that this remains the same. So this shows you that if the object has a velocity which is vy j cap, okay, then that will produce an image velocity which is also vy j cap. Okay, because again the mirror is in yz plane. Okay. So because the mirror in yz plane, this is a tangential component of velocity. This is tangential component of velocity, means parallel to the mirror. So tangential component remains the same, whereas this one, it was a normal component. Okay, that means perpendicular to the mirror. So whenever we have a normal component, it gets reversed in direction. Okay. So normal component of velocity, it gets reversed, whereas tangential component, it remains the same. So in fact, if the velocity of the object was vx I cap plus vy j cap plus even a z component which is coming out of the plane, the velocity of the image would have become minus vx I cap plus vy j cap plus vz k cap, provided of course the mirror is in the yz plane. Okay, so the velocity of the image with respect to the object will become minus 2vx I cap. So this is like the general kind of formula. No, mirror was in yz plane, beta. I showed you clearly above. मिरर इज पैरेलल टू द वाईजेड प्लेन. यहाँ पे एक्स वाई प्लेन ऐसा दिखाया भी है ना बेटा. Mirror is in the yz plane. Okay. So that is why the answer is like this. Okay, now let's see a next level question in this. So in this question, what is happening is we are having say a bus or something which is moving at a velocity of 36 kilometers per hour. It has the back of the bus is a plane mirror. Now we have one person, let's say person A, running behind the bus at a speed of 18 kilometers per hour. Okay, and another bus person B who's at rest. So we want to find the speed of A's image in the mirror as seen by A. Okay. I want to find the speed of A's image as seen by B. Just try this out, people. Yes, Nikita, your answer is correct. Okay, so see, the easiest way to do this question, I'll explain, is that suppose you are in the mirror's frame, you are in this frame, then what does A's velocity appear to be? A's velocity will appear to be like this, okay, because so this will appear to be V1 minus V2 in this direction, which is by the way 18 kilometers per hour. Okay. So then in the mirror's frame, the image of A will appear to move with a speed like this, let's say v prime. So the velocity of the image with respect to the mirror, this is plus 18 I cap. X-axis is and the velocity of the object with respect to the mirror is minus 18 I cap. Okay. So the velocity of the image with respect to the object will become velocity of the image with respect to the mirror minus velocity of the object with respect to the mirror. So that will become plus 36 kilometers per hour I cap. So this is the answer to the first part. Okay. And now you can also see that the velocity of the image with respect to the mirror is plus 18 I cap, and the velocity of the mirror in ground frame is what, plus 36 I cap. Okay, this is with respect to ground. So the velocity of the image in ground frame will be the relative velocity plus the velocity of the mirror. So it will be 18 I cap plus 36 I cap. So this will be the velocity of A's image, okay, as seen by B, because B is at rest in the ground frame. Yeah, the last step is just application of relative motion beta. Okay. Velocity of A with respect to B को हम लिखते हैं ना VA minus VB. वैसे ही velocity of A with respect to C is VA minus VC. Velocity of B with respect to C is VA minus VC. So therefore velocity of A with respect to C minus velocity of B with respect to C is VA minus VB, which is the same thing as velocity of A with respect to B. Okay. Which means that just like we write this, we can also write this. This is a property of relative motion. We should know that if we know two objects' velocity with respect to some third moving object, then we can calculate the relative velocity of A and B by subtracting the relative velocity of A with respect to the third one C minus the relative velocity of B with respect to the third one C. Okay, so this is a trick from relative motion that you can use. So this equation that I've written, this is this one only. The velocity of the image with respect to the object is the velocity of the image with respect to the mirror minus the velocity of the object with respect to the mirror. Okay, so this is the mirror. So this is only the velocity of the mirror in the ground frame. It's 36 I cap. Okay. This is the object. So this is the velocity of the object in the ground frame. So from that we have got this. This is the velocity of the object with respect to the mirror. It is minus 18 I cap. This one. So this is the velocity of the image with respect to the mirror. It is plus 18 I cap. So we got this. Okay, so hope this is clear. So see, what is now actually happening is, when you go back to the ground frame, you'll understand that this bus is traveling at 36 kilometers per hour. Okay. E is running behind the bus at 18 kilometers per hour. So the image of E, now I'm showing everything in the ground frame. Okay, so this image is actually at 54 kilometers per hour and B is stationary. Okay. So that is why you can see that the velocity of E's image A prime with respect to B is 54 I cap only. But the velocity of E prime with respect to A is 54 minus 18. It is 36 I cap. Okay. Velocity of the object with respect to the mirror, you can see, is minus 18 I cap. But the velocity of the image with respect to the mirror is plus 18 I cap. So this is the concept that we use to generate this. Okay. All right. Now let's move on to the next part of geometrical optics, which is refraction. So refraction, as you know, it is defined as the bending of light when it transmits from one medium to another medium. Okay. Both are transparent media. Okay. That means light can pass through them. So that phenomena is called refraction. So as you know, for example, if you have glass, okay, and a beam of light incident like this, then it is observed that as it transmits through the glass, it will bend like this. So this is an example of the phenomena of refraction. So again, if we draw normal at the point of incidence P, so the incident ray, whatever angle it makes with the normal, it is called the angle of incidence. And this is called the refracted ray. Or you can also call this the transmitted ray. Okay. So whatever angle that makes with the normal, that is called the angle of refraction. So there is a relationship between I and R which is called Snell's law. That is the relationship between the angle of incidence and the angle of reflection. Okay. Sorry, refraction. So that relationship depends on something called refractive index, as you know. So first of all, we have to understand the property of refractive index of a transparent medium. So this is generally denoted by the symbol mu, or sometimes you also use the symbol n for it, okay, depending on what. So mu or n, the refractive index, is defined as the ratio of speed of light in vacuum or air with respect to speed of light in that medium. Okay. C is speed of light in air or vacuum, which is approximately 3 into 10 raised power 8 meters per second, or close to 3 lakh kilometers per second. Okay. And V is the speed of light in the given medium. So if you're not familiar with this formula, just make sure you understand this one. We'll come back to Snell's law. First, make sure you understand the definition of refractive index. Okay, mu is greater than 1 always. Okay. So for example, mu for water is 4 by 3. Okay. Remember, refractive index is dimensionless. It's a ratio, so it is dimensionless. So it does not have any unit. Okay, so it's just a ratio. So that means that speed of light in water will be c by mu. So that will become 3 into 10 raised per 8 divided by 4 by 3, or 9 by 4 into 10 raised per 8 meters per second. Yeah, we'll come to Snell's law. Okay. So this is speed of light in water. That will become like this. So this is the significance of this formula. Okay. So that's why mu is always greater than 1. That means V is always less than C. In any refractive or transparent medium, the speed of light becomes less than the speed of light in air or vacuum. Okay, so this is the definition of refractive index. Now this is also called the absolute refractive index, okay, of any medium. That is defined like this. Okay. Now sometimes you also define relative refractive index. Mu is always greater than 1 beta. V can never be greater than C. Okay, V is always less than C, and mu is therefore always greater than 1. Okay. For any material medium, speed of light is maximum in vacuum and almost equal to the same in air, though slightly less. Okay, so that is the idea. Okay, now we also define refractive index of a medium, let's say medium 1, with respect to another medium, let's say medium 2. So we define like this: mu of 1 with respect to 2. Okay, so that becomes nothing but V2 by V1. Okay, so this is refractive index of medium 1 with respect to medium 2. So for example, refractive index of glass with respect to water. Okay. So this will be equal to speed of light in water divided by speed of light in glass by definition. Okay. So now you can also see that refractive index of glass with respect to water, for example, will become, now this is C divided by refractive index of water. This is C divided by refractive index of glass. So it will become refractive index of glass divided by refractive index of water. Okay, where here this is absolute refractive index of glass. Okay, and similarly this is absolute refractive index of water. Okay. So this formula mu of 1 with respect to 2 also becomes absolute refractive index of medium 1 divided by absolute refractive index of medium 2. Yes, Rupesh, that's correct. And Ansh, to answer your question, that is because of the electromagnetic nature of the wave phenomena of light. So happens that electric and magnetic field propagate with their true speed in vacuum, whereas in any medium their speed gets hindered. Okay, so there is a property to do with electric field and magnetic field in any material medium that you will study later. A property of electric field called dielectric constant, and a property of magnetic field called magnetic permeability. So any material medium, it has a dielectric constant greater than 1, which means electric field becomes weaker inside a material medium. Yes, v is the speed of light in the medium, whereas c is the formula, I mean the symbol that we use for speed of light in vacuum. So v is always less than c for any material medium. C is like the absolute value of speed of light when there is no medium present. So the electromagnetic waves are propagating at their true speed without any hindrance from the medium around them. Okay. So as we study more about electric field and magnetic field in class 12, we will understand more about this dielectric constant I was telling you about and the magnetic permeability. And from that we'll understand why electromagnetic waves, they propagate slower in a material medium compared to how they propagate in vacuum. So again, we have to treat these laws as I told you in the beginning, like experimental laws right now. We have to treat them like we have done experiments and from that we have concluded this. So absolute refractive index यही हुआ ना बेटा, it is the ratio of speed of light in vacuum. So for example, if I say what is the absolute refractive index of glass, okay, it is the speed of light in vacuum divided by speed of light in glass. Okay. This is the absolute refractive index of glass. So that I'm denoting with the symbol mu g. So velocity of light in glass, I'm denoting with the symbol Vg. Okay. But when I write this, it is the refractive index is the relative refractive index of glass with respect to water. Okay. So that becomes speed of light in water divided by speed of light in glass. So that further becomes this. So we have the formula that this thing is absolute refractive index of glass divided by absolute refractive index of water. Its meaning is this, but the formula becomes this. is approximately 1 only. Okay. Speed of light in air or vacuum, okay, which is same as, yeah, like it's a negligible difference. That's correct, Nikita. Okay. So now let's come to Snell's law. So we had seen the diagram earlier, okay, that when light is passing from one medium to another, so for example, when it passes from air to glass, it tends to bend towards the normal. But similarly, if it is going the other way, the light is generated underwater, then it will tend to bend away from the normal. So if this is my angle of incidence, let's say I1 now, this will become my angle of refraction R1. So here when we apply Snell's law, so if it is going in the first case from air to glass, then angle of incidence into refractive index of air, which is of course 1, into sine I will become refractive index of glass into sine R. Of course, refractive index of air is 1 because speed of light in air is c only. So sine I in this case will become refractive index of glass into sine R. So you can see that sine R will be less than sine I. That means R will be less than I. So going from air to glass, the light bends towards the normal. Okay. But again, when we look at Snell's law in the second part, going from glass to air. Okay. So this time the incident ray is in glass and the refracted ray is in air. So we will have a refractive index of glass into sine of this I1 will be equal to refractive index of air into sine of R1. So we will have this. This will now show us that I1 is less than R1. So that means glass to air क्या हो रहा है? It is bending away from normal. Okay. Because the refractive index of glass is about 1.5 or 3 by 2. Okay, so this is an example of Snell's law. It's a more general principle and we'll come to that. So what Snell's law tells us that when light goes from rarer to denser medium, okay, then it bends towards the normal, and opposite, when denser to rarer medium, it bends away from the normal. Yes, Piyush, we will be studying, but that will be at a later stage. That is part of the next chapter of optics called wave optics. Here we are doing geometrical optics, which is to do with reflection and refraction only. Yes. Okay, so this is an example of rarer to denser medium. So it bends towards normal. Okay. Whereas this one was an example of denser to rarer. So it bends away from the normal. No, not Doppler's effect. Piyush. Doppler's effect is not part of your 10 plus 2 syllabus. Doppler's effect in sound is there, but not in optics. Okay. Now let's come to the more general form of Snell's law. Okay, so the general form of Snell's law has to do with the fact that we can apply principle of reversibility on light. So if this is any general medium on this side which has refractive index mu1, and on the other side is another medium which has refractive index mu2. Okay. Then suppose mu2 is greater than mu1, and this will tend to be like this. Okay. Now let's say in the first case we are considering this as the incident ray and this is the refracted ray. In the second case this is the incident ray and this is the refracted ray. So in this case this angle is theta 1, this angle is theta 2. In this case this angle is theta 1 again, this angle is theta 2. But in this case this is the incident ray, this is the refracted ray. In this case this is the incident ray, this is the refracted ray. So the general form of Snell's law is that mu1 sine theta 1 is equal to mu2 sine theta 2. And this formula becomes applicable for both. Okay. In the first case and the second case, okay, theta 1 is the angle of incidence. Okay. And theta 2 is the angle of refraction. And the refraction is happening from medium 1 to medium 2. Okay. In the second case, theta 2 is the angle of incidence, theta 1 is the angle of refraction, and the refraction is happening from medium 2 to medium 1. Okay. And you can see here that mu2 is greater than mu1. So this is a case of rarer to denser. In my diagram you can see, and this is a case of denser to rarer. Yeah, you can also express it this way, that's correct, that sine theta 1 upon sine theta 2 is equal to mu2 by mu1. or mu of 2 with respect to 1, whatever implies the same thing. But this is just the easier way to remember it. Okay. So let us just see a simple example of the application of this. So we have a transparent prism made of some kind of acrylic material. So its refractive index is 1.2. Okay, so it's not exactly glass. Glass has a refractive index of 1.5, and this angle is 90 degree. This is a 90 degree angle here. Okay. Now from this side, we are having light incident. Something like this. Okay. So it bends towards the normal first, and then bends away from the normal. See. So now if I draw the normal at this point, okay, this is the normal. If I draw the normal at this point. So this will actually form a rectangle. It's not showing in my diagram that well, but anyway. So this angle is alpha. Let's say this angle is beta. This angle is gamma, and let's say this angle is eta. So given that alpha is equal to 30 degrees, sorry, 37 degrees, find beta and gamma and then eta. Okay. Around it we have air. So refractive index of air is 1. On both sides we have air. So just give this a quick try. This is an application of geometry and Snell's law. Yeah, very good. Alpha is 37, so beta will be 30. Okay. And what about gamma? Okay, so first of all, you can see that this one, this is the first refraction. Okay. So the first refraction is happening from air to, let's say this is plastic. Okay. So to plastic. Okay. So in this, alpha is the angle of incidence. Okay, and beta is the angle of refraction. Okay. So what is happening? Refractive index of air into sine alpha should be equal to refractive index of plastic into sine beta. Okay. So 1 into sine 37 should be equal to 1.2 into sine beta. Okay. So 3 by 5 should be equal to 12 by 10 sine beta. Okay. So that means beta should be equal to 30 degrees. Now once you got beta equal to 30 degrees, what about gamma? Whatever way you write the formula, it's fine, but it doesn't matter. As I said, I prefer to use this formula that mu1 sine theta 1 is equal to mu2 sine theta 2. Now, how we'll find gamma? Gamma we'll have to find by geometry, okay? Because it's still inside the glass only, na, after this, after inside the plastic. So there is no further refraction happening till we come to this relationship between gamma and eta. That is the second refraction. So for second refraction, we'll have a separate formula, but we need the value of gamma for that first. Na? So it is from plastic to air, okay? And there the incidence is happening at gamma, and the refraction angle is eta. So we have refractive index of plastic times sine gamma should be equal to refractive index of air times sine eta. So we have this relation that 1.2 sine gamma should be equal to sine eta. Okay. But we need gamma first. So tell me how much is gamma? 60 degrees. Very good. That's correct. So how we'll get gamma at 60 degrees? So for that you have to understand that if you just extend this and this, because this angle is 90, okay, and here this angle is 90 and this angle is 90. It's a rectangle, so this angle has to be 90. Okay, so if you label these points like if these are P and Q, and let's say these points R and S. Okay, so PQRS is a rectangle, so that is telling you that this angle PSQ is 90 degrees. Okay, so that means angle PSQ is 90 degrees. So therefore, in triangle PSQ, beta plus gamma has to be 90 degrees. So that is telling me now that gamma is equal to 60 degrees. So that's the second thing now. Okay. So as I said, a bit of application of geometry also comes in when we are discussing about prism related questions. Okay. Yeah. So now let us work out. Now we will substitute this here. So from that we should get eta. So let's see what we are getting. So 1.2 times sine 60 should be equal to sine eta. So sine of eta is coming out to be 1.2 into root 3 by 2. So that is approximately 0.6 into 1.73. Okay. So how much is that now? So you can see something interesting. This is approximately 1.038. So sine eta is coming out to be greater than 1. Now this is an interesting thing. It shows you that this is not possible. No? Sine of an angle cannot be greater than 1. So this is not possible. Okay, because sine of any angle is less than equal to 1. So that means something else is happening over here. Can you tell me what is happening? Yes, very good. Total internal reflection will happen. Okay. So instead of refraction at the second surface, what will be happening is what we call TIR, or total internal reflection. So this ray will not be coming out into air. It will be making this kind of. So I'll make the diagram. So instead what will happen is here inside. So instead of bending and coming out, we're doing this. Okay. So the phenomena of total internal reflection will be happening over here. So if this angle of incidence is I, this angle of incidence, I mean R, is equal to I. That is what will be happening here. Yes, there is the concept of critical angle and total internal reflection, which we'll discuss. Okay, so my proper ray diagram now should actually be like this. So remember, whenever we come across a situation where calculation from Snell's law for refraction happening from a denser to a rarer medium is showing us that sine R is becoming greater than 1. That means logically that is not possible. And instead of refraction, what must be happening there is total internal reflection. So here our correct ray diagram will be something like this. Okay. So I'm not concerned at this stage what is happening at the next surface. Okay. But at this surface, this is what will be happening. So this was 30 degrees. Oh, sorry, this was 37 degrees. This was 30 degrees. So this was 60 degrees. So this will also be 60 degrees. Okay. Because for refraction from a denser medium, let's say mu2, to a rarer medium, let's say mu1. So mu2 is greater than mu1. Okay. if the angle of incidence is theta, then mu2 sine theta is equal to mu1 sine of this. Okay. So now if sine r is equal to 1, that is r is equal to 90 degrees, then we say theta is equal to what we call critical angle. Okay. So that critical angle phenomena is like this. When the ray bends just about enough for what is called grazing emergence or normal emergence. So if I'm going from a denser medium mu2 to a rarer medium mu1, but the phenomena happening is this one. This. So then this is called the critical angle because the angle of refraction has become 90 degrees. So this is called grazing emergence because it emerges grazing the surface when angle of incidence is equal to critical angle. So there is a formula for this critical angle, as you can see. So substitute this here. So you have mu2 sine of critical angle is equal to mu1 sine 90 degrees. So the critical angle is given by this formula, sine inverse of 1 by mu2 1. Okay, like this. This is the formula for critical angle. So what happens is if your angle of incidence is less than critical angle, then your situation will be like this. It will be a normal case of bending away from the normal. Okay. So theta is less than critical angle, r will be less than 90 degrees. So it's a case of refraction. Okay. But theta equal to critical angle, it becomes a case of grazing emergence. And as you know, when theta is greater than critical angle, it becomes a case of total internal reflection. If this happens, the angle of incidence is more than the critical angle, then instead of grazing emergence or instead of refraction, this surface acts like a mirror now. And this theta becomes equal to this theta. So for theta greater than critical angle, there is total internal reflection. So it's like a reflection kind of phenomenon. Okay? And the critical angle is given by this formula. Okay. So for example, the refractive index of plastic was 1.2. So critical angle for this one was sine inverse of 1 upon 1.2. So that critical angle you will see will come out to be less than 60 degrees. So that is why when we took theta as 60 degrees, our theta was greater than critical angle. So we are getting total internal reflection. If you do this calculation, sine inverse this is about 56.4 degrees. Okay. So our critical angle was about 56.4 degrees. So that is why over there our angle of incidence being 60 degrees, we were getting a phenomena of total internal reflection. Okay, people, so hope this is clear. Now we'll discuss some more general sort of way of dealing with prism cases. Okay, so there is a sort of fixed method that we have of dealing with the geometry of a prism. This was an easy case of a prism because the angle was 90 degrees, but tell you the more general method of refraction by a prism. So in a case where we are assuming total internal reflection is not happening, okay, just this angle is called the angle of the prism. So in the easy case we had taken it was 90 degrees, but now we'll take a general case where it can be any arbitrary angle like 60 degrees, 30 degrees, 45 degrees, whatever. So if we assume something like this is happening, that the ray from here is emerging, it is not doing TIR. Okay. So in the general notation, and so this is the normal here, and suppose we drop another normal here. So these are the two normals. Now in the general notation, this is called the incident ray, okay, and this is called the emergent ray. Okay. Therefore, this is called the angle of incidence, and this is called the angle of emergence. and these two angles inside here, they are given the special names R1 and R2. Though actually one is acting like an angle of refraction, the other is acting like an angle of um, this thing incidence, but still they are called R1 and R2. Now there is a special formula that tells us that R1 plus R2 will always be equal to A. Now let us understand why that happens. Okay, that happens because once again, if I label this quadrilateral PQRS, this one, and if I label this angle here as beta, suppose, okay. So this happens because in quadrilateral PQRS, you can see these two angles, angle SPQ and angle QRS, they are both equal to 90 degrees each. Okay. So therefore, from the property of quadrilateral, that the sum of four angles has to be 90 degrees. So angle, sorry, 360 degrees. So angle PQR plus angle PSR must be equal to 180 degrees because the sum of the four angles must be 360. So that means A plus beta must be equal to 180 degrees. That's one thing. And now you look in triangle PSR, okay, R1 plus R2 plus beta must be equal to 180 degrees. Okay. So from these two, you get this important property. So this is something you should remember. The derivation is not important. This is something that you should remember. Okay. And once we have worked this out, the rest of the things are very simple because now given the angle of incidence and the refractive index of this material, this is refractive index mu, and around it is air. Okay. So given the first step is Snell's law at first surface. So 1 into sine I is equal to mu into sine R1. So using this now, we find R1. Okay. Now once you found R1, now you use the property that A is equal to R1 plus R2. So using this, you find out R2. Okay. And once you found out R2, again we apply Snell's law at the second. Okay. Once you found out R2, we apply Snell's law at second surface. Okay. And we find out mu sine R2 is equal to sine E. So from this we find out the angle of emergence. So this is the process of finding out the angles. Okay, so just as an example, in the previous question, suppose the angle of the prism instead of 90 degrees, it had been something like, let's say, 45 degrees. It's a much thinner prism. So suppose it had been something like this. This angle had been suppose 45 degrees and mu was 1.2, and once again the angle of incidence here was 37 degrees. Okay. So then what would have happened here is something like this. We would have got our R1 by applying Snell's law, that sine 37 is equal to mu times sine R1. Put mu as 1.2. So R1 would have come as 30 degrees. So that's fine. Okay. Now we would have taken this formula, that R1 plus R2 is equal to A. So we would have got R2 as 45 minus 30. So 15 degrees. Okay. And then we would have used Snell's law again to find angle of emergence, that 1.2 times sine 15 degrees is equal to sine of emergent angle, and from this we would have found out the angle of emergence. Okay, so this is the general method of doing the calculation. Okay, now coming back to that, another important factor here becomes something called angle of deviation, the net deviation. So the net deviation comes like this, that if you produce the incident ray forward, okay, and you produce the emergent ray backwards, okay, then this angle is the angle of deviation. So this delta is called the angle of deviation. That is the angle between the incident ray and the emergent ray. This is called the angle of deviation. Okay, and there's a very easy way to calculate this. So for that, I will label this point here as T, the point which I'm getting when I produce back the emergent ray and the incident ray forward. Okay, so you can see that in triangle PRT, okay, delta is the exterior angle, so delta should be equal to the sum of the interior opposite angles. So that is angle TPR, okay, plus angle TRP. Okay, so that is this angle here plus this angle here. Okay. Now you can see in the diagram that angle TPR is nothing but I minus R1. Okay. And angle PRP is nothing but E minus R2. So geometrically it's evident. This whole angle is this much. Okay. So the angle of deviation becomes I minus R1 plus E minus R2. So it becomes I plus E minus of R1 plus R2. So the angle of deviation becomes I plus E minus E. So this is the angle of deviation. So these are the important formulae to remember when we are dealing with any general prism problem. Okay. The geometrical relation that R1 plus R2 is A. Okay. The Snell's law relations that we use to find out R1, then from R1 we find out R2, then from R2 we find out angle of emergence again. And once we got the angle of emergence, we put this back over here so that we have the angle of deviation as I plus E minus E. So given the angle of incidence, the angle of the prism A and the refractive index mu of the prism, we can calculate all these things. We can calculate R1, R2, E, and then from that finally delta, the net deviation. Okay, so again, in this problem, if we were calculating the angle of deviation, we would get the angle of emergence from this. Okay, we would have got sine E as 1.2 into sine 15. So if you just use a scientific calculator to find sine 15, it's about 0.25 or 0.26 actually. Okay. So then this E would be sine inverse of about 0.31. So if you calculate that, it should come out to be approximately 18 degrees. Okay, 18.1 degrees. So we would have got the deviation as I plus E minus. Okay, so I was 30 degrees. This was about 18 degrees minus 45. Okay, so you would have got about a 3-degree deviation. So this is that kind of situation where the deviation is very less. So something like this is happening. The light which is emerging out is comparatively less amount of deviation. Like it's not evident in my diagram. It should be even less. Okay. Now for extremely thin prisms, there is a special formula for angle of deviation. So I will not get into the derivation of that because we have limited time to discuss optics. Okay. But for a very thin prism, that means the angle of the prism is a very small angle. So typically the angle of the prism should be less than about 5 degrees or so. Okay. We can use a special formula that the angle of deviation becomes mu minus 1 into the angle of the prism. Okay. So if you like, you can go through the derivation of this in NCRT or HC Verma. In fact, geometrical optics is there in HC Verma part 1 only. But you should know this as a formula for your this thing KVPY exam. Okay. So if for example we have a prism which has an angle of the angle of the prism is, let's say, 4 degrees. Okay. And we have an incident beam like this, then it will emerge out from this side with an angle of deviation delta. So suppose the refractive index is 1.5. So then the deviation delta will be this. So it will just be 2 degrees. So this kind of thing. So then, for example, if we have a situation where we have a combination of prisms, so we have one prism like this. This has mu equal to 1.6, let's say, and this angle equal to 4 degrees. And then we have another prism, let's say, but that one is like this, and this has mu equal to 1.5, and this one's angle E prime, let's say, is mu prime, and this one is, let's say, 3 degrees. The net deviation, this, okay. So how do we do that over here? We have to add the deviations. नहीं, mu का value कभी उतना large नहीं होता है बेटा. It can be up to about 2 or 3, but the important thing is the angle of the prism. Angle of the prism should be less than about 5 degrees. Then we can directly use this formula that the deviation by the prism is mu minus 1 into A. The value of mu doesn't matter. It's the value of the angle of the prism that matters. Okay. So what will happen is that this ray will first, let's say, come here with some deviation delta 1 like this, and then in this case it will deviate like this. It will deviate in the opposite direction. Okay, so delta 1 you can see is a clockwise deviation of 1.6 minus 1 into 4 degrees. So it is 2.4 degrees but clockwise, and delta 2 will be a deviation of 1.5 minus 1 into 3 degrees but anti-clockwise. So it will be 1.5 degrees anti-clockwise. So the net deviation now, okay, so if we produce this ray forward and this ray backwards, that net deviation, so this net deviation will be 2.4. Because this is clockwise, we'll have to put this with a minus sign, is opposite. So it will be 0.9 degrees clockwise. So the proper diagram will look more like this. Suppose this ray came like this. Now it bent like this and then bend a little bit like this. So this one, if we produce this back now, this one. So this is the net deviation. This angle is the net deviation. So it is 0.9 degrees clockwise. Okay, so this is about prisms. Okay, so we'll conclude the class, but before that, let me give you a heads up about what we'll discuss next lecture in optics, so you can prepare a bit and come. Next lecture for ray optics, we will have it next week. So in that, we will be discussing two very important formula. One is the real depth, apparent depth formula. Okay, for refraction at plane surface of what we call paraxial rays. Okay. So this is the phenomena whereby, for example, if you're looking at an object which is underwater, okay, but you're looking from directly above, so the observer's vision is of what we call paraxial rays, that is the rays which are nearly parallel to the principal axis. These rays, so these rays, they produce an image which is somewhere here, okay. So that image appears to be at a lesser depth than the actual depth of the object. So the apparent depth x prime is equal to the real depth divided by refractive index of water if it is air outside. Okay, so this formula and its applications we will discuss next time. So the real depth of the object is x, the apparent depth is x prime, which is this. Okay. So this and its applications, this will be an important thing. It's in H.C. Verma part 1. Optics is in H.C. Verma part 1 only. Okay, so you can go through this. Okay. And the next thing we'll go through is spherical mirrors. Okay. So convex and concave mirrors. Okay. So concave, this is concave, this is convex mirrors. So spherical mirrors and the UV formula, 1 by V plus 1 by U is 1 by F. Okay. And thin lenses, convex lenses, concave lenses, and the UV formula. Okay. So these are the three things that we'll be discussing in the next lecture. So if you do a bit of reading ahead, it will help you understand faster. Okay. So that's it for today's session, people. Thanks for attending and wish you all the best.